So the last thing that I wanted to talk about, and maybe is Keng, where's Keng? I thought we could share some learning experiences from what we did when we were trying to get this to work, and some of the things that we thought about, and some of the things we thought about in terms of the network structure. Because you have many degrees of freedom when you're building a network, and sometimes small differences can really be the difference between the network learning something or not. So, and so these are just a few sort of tips for trying to go through some form of sort of reasonably systematic process. So I thought we could wrap up with basically things that we tried and what we learned from what we learned from building this, like the memory distributions and the sort of network architecture. So as a general rule, as a starting point, if my state is in Rn, I will pick a hidden layer that is no larger than your state, your initial state space. Because one way of thinking about what a neural network is doing is it's somehow sort of compressing information from your initial 4 dimensions of state space to a single value number. And by reducing the dimensionality of your hidden layer, you're forcing it to compress information in a useful way. And so you're kind of helping the network out. If you blew this up to say, if you suddenly thought, okay, bigger is better, and blew this up to a 100 dimension hidden layer, you may not end up with such good results because you're not helping the network learn its compressed representation. So it's a general rule, just general rule of thumb, start shallow, so 1 hidden layer. And think about how, so we had our input dimensions were 4 and our output dimensions were 2. So this sort of naturally lent itself to a hidden layer of 4 or 3. And then start with that and iterate, like add more layers or add more depth as it goes. But they're quite complicated to train, so I generally try and get away with the simplest network that I can. One way to sort of try and reason about it is think about how complex the nonlinear function is that your network needs to learn. And generally, the more complex it is, the more layers and the more nodes per layer that you need. But at least start off small and then grow it. I did add a second layer. It didn't add much, and it just made it harder to learn, which, particularly for reinforcement learning, matters because it's not like you have a classic supervised learning problem where you've got those like perfect outputs and you just keep on at it and you're persistent and you can get the network to learn something. The quality of your choices here are affected by the actual network itself, and so the harder it is to train the network, the less likely it is you're going to latch on to that good strategy and learn, because the network itself is governing the experiences and the memory that you actually build. So that's the first one. I started off with stochastic gradient descent, a simple learning rate of 0.01. Up until now, I haven't felt the need to get into fancier optimizers. What we actually found, and maybe I can let you talk about it, is the way in which you sampled from memory makes a huge difference. So that's actually worth spending some time on. So if you can imagine, you've got a sort of memory, and this is your first experience all up to Tn. And you've learned something over time, so the value of revisiting different memory experiences might change. And so actually this is something that made quite a big difference. Memory, so how you sample from memory.
So for example, if you take a look at the current agent right now, it's veering to the right. So when you do random actions at the beginning, there's this thing called the random walk effect. Basically, if you toss a coin many times, chances are the median score, if you average to 2, is going to be pretty far away from the center. So if you start your agent by letting it do some random actions, then the beginning, the early chunk of the memory is going to get stuck doing that thing. So in some sense, you're introducing a bias to that memory, and it's just gonna feed back into the whole learner, and this is what's happening. Like sometimes it happens, sometimes it doesn't. Depends on the chance, basically, the random effect. So one way to get around this is to basically break away from the bias that you get early on from the memory, especially when you do random actions. Well, random sampling is one good one. And if you look at a human, how we learn over time, like if you're a rock climber for many years, or if you are StarCraft players, you tend to forget what you did early back, but over time you evolve your strategy, and you remember the good strategies, right? You remember the useful experience. So you can do something similar for your agent. Basically, pick less of so when you're doing the random batch sampling, pick less memories from the early on memories, and then pick more of those from the closer memory. So like use more of the recent memory and less of the longer, older memory, basically. Yeah.
That's specifically so in the DQ and training, because I asked that before, you're passing old replay memory in, but you're not training every time on every experience you ever experienced.
No, so you sample a fixed number.
From that replay memory.
Yeah.
Is there any strategy where they pick memory that is known that the network did well on that? So in other words, not just practicing on recent memory, but practicing memory where you get good.
Right, but you got to have a heuristic for that too, right? Also, you can't just pick memory with a higher reward, because you have to know what's not good as well to not do that action. So, and you have to, of course, write a heuristic to select that memory. So it's easier to, this is a really easy implementation. Basically, you do a decay graph. Basically, you shift the distribution of picking your memory into, Laura's going to draw the shape. So that's going to be you're going to have less of a chance of selecting the older memory.
Is it linear or curved? Like that? Yeah?
You can imagine basically a normal curve cut in half, shifted to the left,
yeah,
to the right.
Yeah,
Yeah,
like
that's pretty much it. That's the.
Like that.
Got a question there? Yeah. So having memory is different from actually utilizing that memory. So when we train a neural net, we have to pick just a limited number of experience, basically. So that's your batch size, and typically we choose it to be 32 or 64, depending. Yeah. Again, also another thing is that, so if you look at a human, over time we learn to be better and better, and our closer experience. So the type of experience that we get from being better at certain thing is going to get more useful as well. So you learn a certain moves, and you have tried out a certain like really good moves, and you can sample off those really recent good memories. So that is kind of reinforcing on the feedback loop as well. So you are feeding back the learning loop using a more useful batch of memories, basically. Yeah.
Can you explain the batch size and the number of epochs in the code?
You want to go for that?
Yeah. So batch size is how many sort of memories to use in one update of the neural network's weights. It's common to use mini batches as your sort of, there's some theory behind it, so it's called stochastic gradient descent, and it's a noisier update towards the optimum, but the notion that instead of waiting until instead of running your entire data set through the neural network and then updating the weights, you run much smaller subsets and update more regularly. So that's what motivates this. Typical batch sizes are between 8 and 64. Some of the time it's just governed by, so if you're a large network on a GPU, you'll have to really reduce your batch size down. I typically pick 32 or 64 and don't spend a lot of time. 32, between 16 and 64, and don't spend a ton of time working on that part of it. Your other question was around the epochs. So the epochs is actually a little bit misleading. terminology, because an epoch in classic neural network training refers to using an entire set of the data. This is so epochs is, in this setting, it is basically how many updates we want to do compared to how much memory we got. So we actually had a 1:5 ratio in this. So for every experience we got, we sampled 5 times 16 batches from memory and ran that through the network and updated it. Because the updates are small, you'll typically need lots of iterations to the data set in order to converge on a good value. So if you're training a neural network, typically you'll have a few hundred epochs. So this is meant to kind of simulate that, but in an online setting, which is for every experience you get, and it's more relevant. Think of it more after you've had 1,000 experiences, say, and your memory's of size 1,000. For every extra experience you get, you want to make use of that memory. And so 5 was it wasn't precisely picked, but it is some number that is a small number that is a few higher iterations than the number of examples we get. But the sort of motivation behind that was that neural networks typically need a lot of iterations to learn.
What is the loss function here?
It's mean squared error. And the reason for mean squared error, which is actually, I'm glad you asked the question. So our network is outputting a real value. And rather than a sort of classical like category or probability distribution, so mean squared error is, I guess, the most appropriate simple loss function for those types of outputs. If I've got something like a categorical cross entropy is a loss function that's designed for categories rather than real values. So I would just say pick mean squared error for the time being.
Unless you have outliers.
Pardon?
Unless you have outliers.
Unless you have outliers. That I actually don't know much about. I'd love to learn more. What would you pick if you had outliers?
Yeah, one would be using just mean absolute error.
Okay.
Or outliers.
So that's another one to try, mean and absolute error.
What would be an outlier in the context of this specific RL agent in this design?
That is a really good question. So the question is, what would be an outlier in this context?
Rare events, maybe?
Depending on the environment, really. I know. So,
Yeah.
So for simple games like this, it's also depends on what you mean by outlier. Maybe a configuration that's really hard to hit. So for this, it's pretty easy. It's just going to tilt and then move its position. So chances are going to explore all of the configurations you can get for the state. But for something more complicated like StarCraft, for example, there can be so many outliers, like configurations of scenarios that's really hard to reach. I know. I can't give a really good answer for that, but.
Acting appropriately in that scenario actually.
Yeah. So like entirely new situations. So for example, take the breakout game, for example. The agent learned to dig a tunnel and then do something that no human has ever done before. That's an outlier. And, huh? Yeah, I know. It might be able to discover an outlier by exploration, of course, but take some luck, really. Huh? What was the question?
Would a very high score initially also be an outlier?
Again, really, so outlier in a sense of what, like configuration you never seen before, or?
I'm wondering, so in this example where you get a really high score early on, that's actually something that you really want to learn from. And so I don't know whether typical treatment of outliers, say, where you want to exclude them from or somehow deal with them so that they're not sort of affecting the way you're looking at your data. In this case, my sort of reaction to this is that sometimes outliers are exactly the things that you want to be picking up on and learning from. So because they're the sort of, particularly if you're starting off really badly, your outliers are going to be your unusually good outcomes, and there's something you definitely want to learn from. Yeah.
Try putting in regularization of the neural network.
I did, and I didn't find that it helped. I put in L2 weight regularization. Didn't find it made that much a difference. The other option is dropout, which is, not the other option, another option is dropout. But for a network this small, it just didn't really seem, it felt like it would be overkill, really.
Yeah. If you increase the network, you're saying that it tries to do both.
Yeah, but it kind of felt like overkill because it's solving this problem pretty well. But definitely dropout is something to consider. L1 or L2 weight regularization
Especially
to try.
if you go for the breakout game, you're going to have to need that too.
Yeah. So
How do you know that it's overthinking or bias?
How do I know what?
How do you know that you're overthinking or there's high bias in this analysis? How do you raise that those here?
So the question was, how do you know if there's overfitting or bias, which is sort of a classic problem that neural networks face. Again, I'm pausing to think about it because a neural network is playing your sort of overfitting and bias, sort of very important evaluation metrics when for classic supervised learning tasks, when you can, there are ways of describing your relationship to how you perform on the test set versus your training set. In this case, we don't have the same setup. So we've got a sort of online learning problem that really our feedback mechanism is how well we're performing in the environment. And so I feel like there's a bit of reframing which is needed, which is you can't really directly evaluate them in the same way.
If it took an action that was like locally really good, but it kept driving it to do something that was, maybe that would be a overfitting in some context.
Yeah, I think that, so the suggestion was that if you're constantly doing a locally sort of optimal action that is mean you're just not really doing very well overall, perhaps that's overfitting. I think that's a good way to look at it. Yeah.
One example could be if you like cancel to one side and then just kind of like move it across.
Yeah.
Continue doing that and not trying to.
Yeah, but that's more bias, right, than overfitting, where you're kind of skewing, always going in one direction.
Also, I've seen scenarios where it plateaus at reward 100, so that's by doing the tilting over, just keep on driving it to the side, and it thinks that that's the best it can do. So that's another thing to look out for. It also has to do with how you design the reward signal, because it doesn't quite tell if this is good or that is good. So that comes in the design of the whole system too. So there's a lot of things to consider as well.
Yeah, so this reminds me, so with the cartpole problem, there's actually almost two problems, which is don't make it fall over immediately, but since you've got a game setup which terminates after 200 episodes, it's almost like they have to learn how to keep the pole upright and then how not to run off screen. And so often what you'll see is it figures out how to run it upright first and then start running off screen, because there's nothing in the environmental setup which sort of running off screen when you were doing badly kept you alive for longer, and it's only after you start to do better that then that becomes a less good option. And sometimes you'll see the network it'll learn to keep it stable for a bit, then start to creep, and then it'll have learned how to run right to the edge of the screen and not off. And again, because it's part of the way it's designed, there's nothing to say that that's less good.
Right. Also, because if you solve the problem by balancing the whole thing in the middle or versus veering off the screen very slowly, that's still considered like the same. That's still a solution to the problem. So one way to get around that is to basically increase your time step to maybe 400 time steps, and then maybe if you do that long enough, it should be able to balance the stick forever. That would be a true solution. Yeah, that could work too. I think. Yeah.
I think we have to start. Yeah.
Sorry?
The reward is constant, right?
Per step, it's just 1 and 0, so it's really, it doesn't tell much about the other. So our time is up almost, but if you got questions, feel free to approach us, like behind the scene, whatever. But yeah, I hope you guys enjoyed this session, and let us know how we did. Like if you want more of this, or if you want to do something else from the repo, like extend it, whatever, apply it to something else, feel free to reach out. You can find me on Twitter and Laura on Twitter as well. Yeah,
Cool. Thank you very much.